Hello, cowboys and cowgirls. This is Dr. Johnson. I'm one of the AP Stats teachers at Capel High School. Welcome to today's lesson on the geometric distribution. First thing I want to do for you is to distinguish the binomial distribution from the geometric distribution. In a binomial distribution, X counts the number of successes obtained in a fixed number of trials. How many baskets can someone make in 20 attempts? In a geometric distribution, the random variable y counts the number of trials needed to obtain that first success. So the problem is asking you, what is the probability that the first success occurs on the nth trial? Then we're talking geometric distribution. Examples include rolling a die until you get a 3, attempting 3-point shots in basketball until you make a basket. Now, what are the conditions for having a geometric distribution? Here they are. Y is called a geometric random variable with parameter p, that's the probability, if all of the following hold. First, y is the number of trials required to obtain the first success. So the range of y could be anything from 1, 2, 3, 4, and so forth. You could have your first success on your first trial, for example. Binary, there has to be only 2 possible outcomes, often it's called success and failure. Independent, the trials must be independent, and the probability of success must be constant. If all of those conditions hold, then y follows a geometric random variable with parameter p. Now, if y follows a geometric distribution and and the possible values for y are 1, 2, 3, and k is one of those values, the probability that the first success occurs on the kth trial is given by this formula. Now, this formula is not on the AP Stats formula sheet, but I think you'll find that the probability calculations come pretty easily from basic principles that you already know. Notice here that we have k minus 1 failures followed by 1 success. So the probability that the first success is on the kth trial is the probability of failure, 1 minus p, to the power of k minus 1 times p, probability of success. That's our formula for geometric probability. Let's use it in an example. Suppose you roll a fair 6-sided die. What is the probability that the first 4 occurs on the 3rd roll? So we're going to roll it until we get a 4, and we're wondering, what is the probability that that first 4 is on the 3rd roll? I'm going to first define my variable y as the number of rolls needed to roll a 4. I need to check whether this follows a geometric distribution. So I ask myself, are the outcomes binary? Yeah. Either I roll a 4 or I roll something else. Are the trials independent? Yes. If this is a fair die, the trials should be independent. Is the probability of success constant? Yeah. The probability of rolling a 4 remains constant at 1 out of 6. In that case, then y is distributed following a geometric distribution, and the parameter is the probability 1/6. Now let's go ahead and do the math. What is the probability the first 4 occurs on the 3rd roll? I plug my numbers into the formula, and that's what you're going to have to do. To show your work, you have to plug the numbers from the problem into the formula. In this case, the probability that the first 4 occurs on the 3rd roll, so probability that y equals 3, is the probability of failure to the power of 2. We have 2 failures, and then that's followed by 1 success. So I multiply that by the probability of success. And I can put that directly into my calculator, and I get probability of 0.1157. But I'm also going to, so then I want to show you the calculator notation. I want to show you how to do this on the calculator, but when you're doing this kind of a problem, I also want you to put in your calculator notation. And in this case, the calculator notation is geometric PD with x equal to 3 and p equal to 1/6. That's my calculator notation. So let's get out your calculator. If you don't have your calculator out now, pause the video and get it. We're going to turn our calculator on. We're going to go to the stats menu. That's menu number 2. You want to hit F5 for distribution. And then we're looking for the geometric distribution. We don't see it there, so we're going to hit F6 so we can see the next soft menu. And there we see geometric, geo. So you hit F2. And since we're trying to find the value probability that y is equal to some value, we want to use the geometric PD, the geometric probability distribution. When you get to that screen, you're going to want to select variable. And now we're going to input the value for x and the probability. So I input x equals 3. My probability is 1 divided by 6. I can just type that in, 1 divided by 6. And the calculator gives me that decimal form. And when I have that, I hit execute, and it tells me the probability, p equals 0.1157. So I go back to my problem, and I put in probability 0.1157. Now, I should tell you that this right here shows you all the information that we want to see whenever you have a question on a probability distribution. On all questions involving probability distribution, I want you to define the random variable. I want you to name the distribution. Here we have a geometric distribution. I want you to tell me the value of the parameter. In the case of the geometric distribution, there's only one parameter, p equals 1/6. Then I want you to have your probability distribution with the formula, with the numbers from the problem in the formula, and your answer. And finally, I want you to have your calculator notation. I want all of that in your answers. I want to show you another example. This is example number 2. Suppose you roll a fair 6-sided die. What is the probability it takes 3 or more rolls to get a 4? 3 or more rolls to get a 4. So now, just as before, but this time my probability expression looks a little bit different. I'm trying to find the probability that y is greater than or equal to 3. I want to find the probability that y is greater than or equal to 3. Now I could write this out. I could write the probability that y equals 3 and put that formula in, plus the probability that y equals 4 and put that formula in, plus ... That's one way of doing it. Or else I could write it rather quickly using this notation here. And this is saying I want to take the sum as k goes from 3 to infinity of this expression. So I have the probability of failure to the power of k minus 1 times the probability of success. When I add them all up together, I get 0.694. My calculator notation here looks something like that, geometric CD. But now I have to describe the low and the upper. These are the lower values for x and the upper values for x. Now, our calculator you can't put infinity into our calculator, so I pick an arbitrarily high number. I picked 1,000. So let's go and see how this looks on your calculator. Here's your calculator. To get through this menu, you're going to go to stats. That's the second menu. This is a distribution, so hit F5 for distribution. To find the geo, we have to go to the next menu, so hit F6. Now hit F2 for geometric. And now we want to pick GCD. We want the geometric cumulative density function because we're looking for probability over a range. When you get to this screen, we want to select variable, and now we're going to input the lower and the upper values for x and p. As I said, my lower value is 3, my upper value is 1,000, and the probability is 1 divided by 6. When all of this looks right, I hit execute, and it tells me the probability is 0.6944. I go back to my problem right here, and I put 0.694 as my problem. I write down my calculator notation, and I'm done. Now, I want to talk a little bit about the mean and standard deviation of the geometric random variable. If y is a geometric random variable with probability p of success in each trial, then the mean or expected value is 1 divided by p. And if you click on that link, it'll take you to a proof. That is, the expected number of trials required to get to the first success is 1 divided by p. In our example, what is the probability? We want to find looking for the probability of the number of trials until we got our first success, that is rolling a 4. Well, since the probability of rolling a 4 was 1/6, our mean was 6. And that shouldn't be surprising. If we think that if the probability of rolling a 4 is 1 out of 6, then on average we would expect that it would take 6 rolls to get a 4. We love to test you on interpretations, and here's the interpretation. In many trials of rolling the die until we get a 4, the average number of rolls it would take to get a 4 would be about 6 rolls. Okay, now let's talk about the standard deviation. If y is a geometric random variable with probability p of success on each trial, then the standard deviation y is given by this formula. And my interpretation is this. In many trials of rolling a die until we rolled a 4, we would expect that the number of trials needed until we rolled a 4 would typically vary by about 5.477 rolls from the mean of 6. Now let's talk about the shape. The mode occurs on the first trial. Okay, so the geometric distribution always starts high and declines rapidly. The mode occurs on the first trial. They're always skewed to the right, and the probability decreases as k increases. Okay, as p decreases, as p gets lower and lower, smaller and smaller, then the distribution decays at a slower rate. If p is large, it'll decay at a very high rate. So I have two graphs on the right hand side. If p equals 4, if probability is 0.4, it will decay right quickly. If probability is 0.125, it decays at a much slower rate. So let's compare the binomial setting versus the geometric setting. They are very similar. The difference is in the lines that I've highlighted in red. So with the binomial setting, the number of trials n is fixed in advance, and in the geometric setting, the variable of interest is the number of trials required to obtain the first success. Here are some testing suggestions. You may pause the screen right here. We may come back to that right before the test. Thank you for watching today's video.